Okay, it's great to be back. Let's start a little belatedly, but once you have Italians in the mix, you can build schedules, which I find very upsetting. I live in Germany, so this is so any mistakes in my talk, it's the Italians' fault. So some of you may remember me. I've talked here last year. I liked it so much that I came back, and apparently the organizers liked it so much that they invited me back. Last year I talked about the same topic, just more generically. I spoke about logging, metrics, and error reporting. And from all those topics, metrics seemed to be the, let's say, hardest part, because there was no clear answer to how to do it. And after I've delivered this talk at EuroPython, someone approached me and told me about Prometheus, which I heard before, but then I started really getting into it, and then I understood it, and then I loved it, so this year I will be diving into this subtopic. Now I still work at the same place, at a web hosting company. I'm doing infrastructure there, so metrics and monitoring are a big part of my work. And since I have a lot of material to cover, so poi kali, and let's talk about the goals of my talk. And by the end, I want you to be able to predict performance problems, so you can prevent them, because stomping out a blaze is much easier than fighting a huge fire. If something happens anyway, I want you to be alerted by your system and not by your hysterical boss. And if a fire is already burning, I don't want you to stare at a top output while your boss is poking their finger into your bag, but I want you to have all the data accessible to you in a meaningful format, so you can query it and find out what the hell is going on and what you can do about it. And this also includes historical data, because in post-mortem you want to be able to reason about how you got there where you are. How did the situation even happen? And if you want to talk about situations, you need an objective representation of the situations. Because then you can describe what's a good situation, and you can describe a not so good operations fire. And you may have guessed what objective representation is gonna be. Right, this is true. It's of course metrics. And metrics are just numbers or samples that are time-stamped in a database. And to make them even more useful, you will have a lot of them, because once you start correlating metrics, they have a lot more meaning. And you get those by adding instruments to your system. It's just the same like in a plane or in a car, except that your instruments that you add to your software are hooked up to a time series database. And this time series database will store them and will allow to do queries and operations on top of them. And what do you instrument? Obviously you will instrument your app. Then you want to instrument your dependencies, like your databases, your load balancers, web servers. They all carry very useful information. You want to have that. You want to instrument your environment. You want to know the server load. You want to know the network congestion. You want to know if the I/O is going out of whack. And finally, you can also instrument your business. Things like number of customers, number of paying customers, because in IT it's not always the same. Sign-ups per day, daily revenue. Because seeing a graph that correlates your front-end latency with user sign-ups can be enlightening under certain circumstances. And nothing of this is really new. People have been doing this for years. I've been doing this for years too. But until now, you had to choose multiple components. And each of these components have certain drawbacks. And you have to learn about all of them to decide what you're going to use. And they're also not really integrated. So InfluxDB or Graphite, they are just storage. They do not care how the data gets in, and they also don't offer you anything really to do monitoring on top of that data. And others, like StatsD, are more or less broken by design, because if you rely on UDP, this is a problem, because once you get hit hard, that's one of the first things that may go to ashes. And this microphone is really too sensitive to
raise it up a little bit. Yeah. So your air is coming
Can you
down.
still hear me? No. Okay. Again, you don't want to use UDP for mission critical data. So Prometheus is different because it gives you a well-rounded and opinionated metrics and monitoring system, and it's still completely flexible, but it gives you a proven and well-documented starting point, something people have been missing all these years. And opinions are dime a dozen, but in this case they are actually worth something because it's heavily inspired by Google's internal monitoring system called Borgmon. And it was indeed written by ex-Google engineers who were missing their beloved monitoring system when they went to SoundCloud, actually. So it came out of SoundCloud, but it's spreading everywhere right now. And now we will have a small architecture walk, so you have an idea how this how it works in general. So Prometheus is just a single binary, so you may have guessed what language it's written in.
No.
It has no dependencies. You just need a configuration file and everything just works. Its central feature, of course, is the effective storage of time series. And what they actually are storing is just a named stream of float samples with a timestamp. That's all. A name, floats, timestamps. But Prometheus wants you to think in terms of 4 types, which are built on top of this simple type. So first there are counters, which is for counting events, requests, errors, whatever. And counters can only increase, so you cannot decrease a counter, but they can get increased by anything, because they are floats. So you can use it to measure your outgoing traffic, for example. Then there are gauges, which are for exposing numbers, concrete numbers. This can be the server load, this can be some temperature, this can be the number of active requests, or the status of a connection pool, which is my favorite usage for gauges. And those two have a pretty obvious mapping to a stream of floats. A more complicated thing is a summary, which takes measurements and allows you to compute the rate and the average on top of these measurements. Some client libraries for Prometheus, and Python is explicitly not one of them, also allow you to define percentiles. The problem is I do not find this type very useful, because you cannot aggregate percentiles. It just doesn't work mathematically. It's not a meaningful operation you can do. And also it adds server load. If my application is screeching from load, I do not want it to be busy deriving numbers. And that's where the final type comes in, which is a histogram. A histogram works similarly as the summary. It takes measurements, it observes them, and it's computing averages and rates. But additionally, you define buckets. And those buckets should represent numbers in which the values you are measuring fall into. And then Prometheus can estimate percentiles from those buckets on the server side. So the heavy math is not done within your app. And I've said percentiles twice now, and that's because they're very important. And to make sure that we're on the same page, I'll do a quick primer on them. And we'll start with a premise, and that's that averages are probably less useful than you may think. And to have something concrete to talk about, let's assume that you are measuring request times. And I think it's fair to say that they are a big part of the user experience. Because fast requests are good UX, and slow requests makes people give up on your page. So, now the problem is that the average time is not the average user experience, because there's no such thing as the bell curve in production. Production data is always skewed to in some ways. So, for example, if you take this, 2.8 is not the average experience people are having. Nobody's actually having 2.8. So not only that, but it's also hiding the terrible UX of the 1. So there's an outlier, and you don't know there is an outlier. You just know that the average is kind of okay. So, what is the average user experience here?
10.
No. It's 1, exactly. So, and if you recall high school, there is a function that would have told you so. And that's the median. The median takes a sorted data set, and it takes the middle value and returns it to you. Or if it's an even numbered set, it takes the average of the two middle values. Now, the median strength of representing the average experience for a user is also its biggest weakness, because this still returns 1. Yeah, it's a 100,000 instead of a 10. So you have two requests, 1 millisecond, 1 millisecond, 100,000 milliseconds. The average user experience, or the median, is still 1. So clearly, the median is not useful by itself either. So, but fortunately, where the median comes from, there's much more. And that brings us back to percentiles. And they also take a sorted data set and they partition it, this time into 100 partitions. And then you look at the nth value for the nth percentile. So basically, the nth percentile p of a data set is bigger than n% of the values. Now, this sounds too weird for a talk, so let's see what it means in practice. It means that if the 50th percentile is 1 millisecond, then 50% of your requests are done by 1 millisecond. Okay? Which makes it the median again. Which we've already established is not super useful, but now we have a parameter we can tweak. And now we can ask, how long did the 95% of our fastest requests take? And then we get 90,000. Which tells us two things. First, it has to be some interpolation, which makes sense because we do not have 100 values, so it does have to do some interpolating work. And secondly, you see immediately there's something going wrong. And it's something that does not affect at least a half of your customers, which is a very useful information to have. If you would go with an average, you would have a big number, and you would have no idea that super few people are affected. So you maybe would be wasting your time to optimize your average case, which is super awesome with 1 millisecond, and would not spend the necessary time on looking for the outlier. So 5% of our requests take, at least 5% take virtually forever. Let's look at a graph from production. So this is really live data from us, and from the bottom to the top we have the median, the 95th percentile, and in blue it's the 99.9th percentile. And you can see two things. First, the 99th is very volatile, which makes sense because it's the one slowest per mil of all requests. There can be so many reasons why they get so slow. So they are really, you have to still watch it, but you cannot, it's not that useful for day-to-day operations. Then you can kind of see that there's a connection between the median and the 95th. So let's remove some noise and look at that. And you can see that those dens are mirroring each other. So that basically means that in these cases, the user experience for 50% of the requests improved, but 5% got worse, and a lot worse in times like times 2 or times 3. And this is again very useful information to have because you know who are affected. And of course you can ask for any percentile, so you can narrow it even further down. Percentiles have one downside, and they are rather complicated to compute. So it's good that Prometheus is doing that outside of your application. There's one then that has no mirroring, and this just means that the median got better, and if something got worse, then it's less than 5%. So again, useful to know. And now let's look at metrics naming. If you've used Graphite before, so anyone used Graphite? Okay, so I'm sure you've seen something like that. you put all the data, all the metadata into the name, and your actual metric name is hidden somewhere in the middle. So Prometheus, as any modern TSDB nowadays, uses bare names. It's best practice to use the application name as a prefix. This is not a good application name. I just want to use a big font, so it's short. And the unit as a suffix. So total is used for counters. If it would be a timer, you would say seconds, if you measure in seconds or microseconds, depending what the actual unit is. Now, you add the metadata using labels. And each new label combination still adds a new time series. So you have the same amount of time series, it's called dimensions. And this is much more readable. First, because you see on the first side what is the actual name of the metric and what are the dimensional definitions. Then it's structured, which allows you to work much easier in aggregations. You can write regular expressions on top of label values and things like that. So Prometheus is really powerful in that thing. And now we come to the kicker. Where does this data come from? And Prometheus is contrary to most metric system pool-based. So that means that each instrumented system exports its metrics using HTTP, and Prometheus comes regularly and scrapes it and writes it down. So yeah, that's what it means, and it has a bunch of consequences. So first, it means that you can adjust the resolution of your data for each target, so you don't have to have one resolution, by configuring how often these metrics are scraped. So you can decide for yourself how you want to trade off disk space versus precision. Then, if a scrape fails, your data does not become less useful, you just lose resolution, which you have to compare to a metric system where if you start losing samples, your rate is ostensibly going down, although it's rising beyond its capacity. So this makes Prometheus really, really great for monitoring, but it's a bad fit for something where you need every single value. And then you have to use something like InfluxDB or Postgres, because Prometheus is not made for this. You will never get the single values you've measured. So this has a few problems. So short-lived jobs. If you have a backup script, you're not going to write a daemon that's running all day, so Prometheus can scrape it. For this, there's a so-called push gateway, where short-lived jobs push their data into it, and Prometheus just scrapes it from there. The next problem is target discovery, because if you want to scrape your targets, you need to know about them. And one approach is to do it using configuration. This one just tells Prometheus to scrape itself, which gives you the number of time series or how the buffers are full. This is very useful if you want to tune the storage engine and the memory usage and things like that. Now, a metric endpoint you are scraping is called a target or an instance. And it's basically a tuple of the host name and a port. And a set of those targets, because you can have many, which are the same type of system, but like multiple backends or multiple Prometheus servers, are called a job. Now, you get these two values, you get applied to every single time series automatically, so you can keep them from each other as labels, which means that you can use the same metric name everywhere, which is especially useful when you are instrumenting your internal libraries. Now, this is one way, but in production you usually want to use some kind of service discovery. Prometheus allows for a lot of them. We personally are using Consul. We are from HashiCorp. We are super happy with that, but people are using a lot others. Now there's one final problem, and this is the only actual problem. If you need to scrape the metrics from your systems, you of course have to have a way to expose them. So something like Heroku or systems running in a customer's closed-off network, that's not gonna work. So, generally speaking, Prometheus is intended to run in the same network as its targets. Okay? So, depending on the use case, I understand this can be a showstopper. So if that's for you, and you want to have coffee, you can leave now. There's no hard feelings. I do realize that Prometheus is not for everyone due to this property. It's always a trade-off, and yeah. With that out of the way, let's talk about some advantages. So the one is, you can point multiple Prometheus servers at the same targets. Now that gives you many benefits. For example, you can have high availability, which is pretty nice for a monitoring system or a metric system. And of course it means that you can have production data in development. You just start Prometheus on your notebook and you point it at your metrics endpoints and you can play with actual data. And we did that when we had an intern, which we asked to do some Prometheus work for us. And we never allowed him to touch even remotely our monitoring system. But we gave him access to the metrics endpoints of our targets, and he just ran his Prometheus on his own notebook and could do any work he needed. This is a very useful property. Then, speaking of monitoring, if a scrape fails, you immediately know there's something going on, there's something broken. Either it's a timeout because the system is too busy, or it's just down. This is much easier to reason about than if you have a push-based system and you have to guess, how long did I not hear from this target? Is it idle, or is it down, or is it just dying right now? You cannot really know it, and you have to implement something like heartbeat systems or something. So this is much easier with pull-based approaches. Then finally, instrumenting third parties is actually pretty easy. No, sorry, I skipped that one. I like this too. If you send out a metric whenever you get a request, your metric traffic is rising with your actual traffic. So you're basically contending for network resources and for computational resources due to the fact that both curves are rising. With Prometheus, it's always the same. You configure how often the metrics are scraped. Prometheus comes around and it's always the same effect. Yeah, as said, if you start losing samples because you hit really hard, your metrics become completely useless in the worst possible moment. Now it's time for third parties. Third parties are easy to instrument because any production system has some kind of performance counters. And you can read those out and just expose them in the Prometheus format. So databases have usually some kind of tables, web servers have status pages, Java has JMX, and you just transform them. And you transform them into something that you can actually read too. So this is the first part of a histogram. And it's made for measuring latencies, which again is not a good name. Please give your metrics better names, but I like to use a big font. Now, it consists of multiple timelines, and this is just the first half. So first, we have a counter of how many values have been observed. So how many requests. And then the sum of those measurements. So the total time observed. So we had 390 requests, which took in all completeness 177 point something seconds. And this is literally what Prometheus sees and what it stores. This is super cheap to keep track of because you are just increasing float numbers. But with those numbers scraped regularly, Prometheus can compute the rate by which they are rising. So you can compute the requests per second, and you can compute the average request times, which have problems but are still useful. And this is what you get when you are using the summary type in a Python client library. These two numbers, these two time series to be better. So now we want percentiles. So let's look at those. These are buckets. We have 6 buckets. And the LE label is the upper limit of this bucket. And this is of course the number of values that have been observed that fit into this bucket. And they trickle down, of course. Something that fits into 0.5 also fits into 2.0. And Prometheus now can interpolate the percentiles from these numbers. That's good enough in practice, and you can increase the precision simply by adding more buckets. And it's still pretty cheap. You're just comparing a few floats and adding a few floats. But of course, you have to make sure that your values fit evenly into these buckets. If you make your buckets for times you wish for, and all values are just in plus inf, you have a problem. Prometheus cannot compute anything meaningful out of that. So you have to look at your values and try to get an even distribution of the buckets for that. Now, we have metrics in a database. So what do we do with them? And we will query them. And we do that using the Prometheus query language called PromQL. I could make a whole talk just about PromQL. You can do the game of life in it. It's pretty amazing. But let's have a few examples. So first, if you have many related time series, you want to aggregate them to a few or a one. So say you have many backends in multiple data centers. Now you want to know what the total sum of all backends is. And yeah, you want the total request rate, let's say it like that. And this is how you would do that, and let's work ourselves from the inside out. First you take the counter, which you should remember from the slides before. And to compute the rate, you use a so-called range vector. So this will return a set of values of the past 1 minute. How many that are depends on the resolution of your data, but that's what it does. The values of the past 1 minute. And rate takes the first value and the last value and returns you, computes how fast this value is rising or falling. At that point, you have the rates for all your backends, or all combinations of labels. And to get it down to one value, you use the sum function. Done. Now, what if you want to know the rate of backends for just one data center? And that's where labels come in. This is a so-called filter, and it works. Everything works just the same, except that only time series that have DC set to west are going to be summed up. And finally, maybe you want to know the rate for all data centers, but you want to have it broken down by data center. And then you drop the label filter again down, and you tell the aggregation function to retain the DC label. So that's all. Let's look at what's else interesting, and of course it's percentiles. And Prometheus uses so-called phi quantiles, which are basically just percentiles divided by 100. So this is the 90th percentile. And now we take the rate of how fast the buckets we defined before are rising, and histogram quantiles will do all the rest. So naturally this will give you the 90th percentile for all label combinations you have, so you will probably want to aggregate them in some form. But there's that. We have our percentiles. This is how you do it. Again, it's just an interpolation, because to produce the real percentiles you need all the values, and you need to partition them and look at them. But it's good enough in production. This will tell you what you need to know. Now, another gold nugget I really like is the top K function. And this is just an example how the web interface looks too. And it returns the, in this case, 5 highest values for time series. So here I ask the load of all hosts, and it's actually 11.81, and the host is H-005A. We are on metal. We are real metal. So I hope you can see that it's really a powerful tool, PromQL. And this tool is used by all other consumers, most notably, of course, visualizations. So there's the internal one, which is not pretty, but at least it's not XJS. And yeah. It's great for playing around and drilling into your values, and for building queries that you build elsewhere, because it's native to the time series. But it allows only one expression per graph, so you cannot correlate unrelated time series. But you can build dashboards using Go templates, which I would rather discourage you from. Another alternative that used to be good because it has the best integration and is the former official one is PromDash. But after Grafana merged Prometheus support, it's deprecated and you shouldn't bother. I just wanted to mention it. Instead, use Grafana. It's the best and best looking dashboard software right now. It has many integrations, which means you can mix and match. So if you're running Graphite, you can just replace single graphs with Prometheus graphs, one by one. And this enables you to do a step-by-step adoption. You do not throw everything away. You can just start slowly. Use this. But you probably already are, because it's amazing and everybody loves it. So, piece of the puzzle, of course, alerting. So you can use the PromQL I've already talked about to formulate alert conditions. And then Prometheus will push them into an external daemon called Alert Manager. And it's, again, time for examples. So, let's talk about monitoring for full disks. Because once they're full, it's too late. And alerting on a threshold, like if you say 90% or something, can lead to noise, because just because it's over 90%, if it's growing by 1 byte a week, it's still not going to fill up anytime soon. So you will probably suffer from alarm fatigue. And alarm fatigue is really bad thing, because it just means that at some point you will underestimate some problem and everything will go up in a fire. So let's use a crystal ball and be notified in time without noise. And for that, we define an alert that will warn us 4 hours before our hard disk is going to be full. And here's our crystal ball. It's high school math again, and it's the linear regression. So, given the samples, again, a range vector of the past 1 hour, if the capacity is expected to be below 0 in 4 hours, and this estimation is true for 5 minutes, we want to be alerted. Okay? Now, how you get alerted depends, because Alert Manager integrates with a lot of possible backends. It supports, of course, email, PagerDuty, but also webhooks, which gives you Slack or anything else. You can write your own integrations. So far so good, but how do you make all of this web scale? The answer is federation, because a Prometheus server can get their data from other Prometheus servers. So you can do aggregation. So if you have a lot and lots of backends, maybe you want to pre-aggregate your data per data center or per host, per whatever. And then you have one big Prometheus that aggregates this data from those Prometheus servers. So you have a hierarchy of aggregation. Or you can use it for downsampling. So maybe you have a really fast computer with a really fast SSD, which is scraping a lot of data very fast. But it keeps them only for like a week or something. But this is really useful maybe for graphing and alerting. But you want to keep some data. But you do not need this resolution, and you cannot afford so many SSDs. So you just set up another Prometheus server with a lot of storage on spinning disk or whatever, and you sample this data from the fast one at fewer intervals. So you get a lower resolution, but the data is still valuable, and you can see historic data. That's about the architecture. I hope you have a general idea, and let's focus on how to get data into this system. And we start with the environment, because it's the least intrusive. And Prometheus has been now out for over a year. So it's much older, but it has been marketed or pushed forward by its makers for at least a year and something. And I've pointed already out that it's easy to write integrations, and so there are a lot of integrations. And one interesting part are, of course, so-called bridges. So if you are using StatsD or Graphite, you don't have to touch your software at all. You just install a Graphite exporter, you point your software at this Graphite exporter, and everything keeps working like before. You do not have to change anything. And the same for StatsD, CollectD, or InfluxDB. We still also have old remnants of our older metric systems. For example, because there are some exporters in CollectD that are lacking for Prometheus, yeah, you keep using CollectD. It's all easy. You can do step by step, and it works great. But of course, native is better. So let's start with platforms. And for fully featured servers, like Metal, KVM, or LXC, you're going to use Node Exporter, which is an official project of Prometheus. And you know what comes next. For Docker, you're going to use CAdvisor, which instruments from the outside. That's a big difference. Node Exporter runs on the server it's instrumenting. CAdvisor runs outside of it and talks to the API of the host, of the container, to get its metrics out. Now, if you install something like this, you get immediate system insight of all your servers. You get things like the load, the number of processes broken down by status. You get your free memory, network saturation, how full the disk is. We saw already some examples how it can be used. And of course, your I/O load. So all things you want to maybe correlate with your slow requests. But there's more. So there's the boot time, so you can do queries on how long is the server running. And there's also service manager status things, so you can check whether Upstart was able to start something. So I think it's important that this is part of your automatic provisioning, as it is for us. Another nice way to do that is called Mtail, which comes from Google. And Mtail will follow a file, and it will compute metrics on the fly using regular expressions. And it turns out that in some cases, like the Apache web server, you can get better metrics by using a custom log format and running Mtail on that than you can get from its status page. Okay, so you should definitely check it out. We, for example, as a provider, are using Mtail heavily on our mail logs. So we get useful information, how our mail systems are behaving, how much spam is coming in right now, how much are we graylisting. And there's so much more. So if you like ping them but don't want to pay for it, there are like box exporters which will probe your system using HTTP, TCP, or even ICMP, so ping. They create additional load, which may or may not be a problem for you. Then no matter how you do it, whether using the status pages or using the logs, you should always instrument your outer edge of your system or your infrastructure, because that always gives you useful information. And that usually means web server or a load balancer. Now, every application nowadays has some kind of a database, so there's a lot of instrumentation too, even for things I don't consider a database, but some people here do. Instrument them if you use them. It's very useful. So we now have detailed information about our platforms. We know how to look at our application from the outside by analyzing its logs or by probing it. And we know that we can instrument our dependencies, and probably someone else did it already for us. So assuming you instrument your web server, so the edge of infrastructure, you can already correlate request times with platform metrics and with dependency metrics. That's already pretty good, but now it's time to touch our precious code. And yeah, there's a first-class Python client library directly from the Prometheus people, and we will use an example. So let's assume you've built a groundbreaking product that will take a photo and tell you whether it contains a cat. So now you want to deploy it as an HTTP service where people will post a picture and your service returns meow or nope depending on the contents of the picture. So, how hard can it be? Let's write a Flask web service. And you don't really need to know Flask very well, because I don't either, or even Python, but I can presume it here, I think. And this is just simple. You check the authentication, and because you read Hacker News, it's a microservice. And you have an expensive computation, which does the actual work. And I bet at least some of you have already written APIs like this. You just have some functionality, you slap up a Flask on it, and it's live. Now let's look how to instrument this. And again, there's the official client. And before we change any code, we do the least we can do. We just start the HTTP endpoint that comes from Prometheus. And that's because on Linux, you get process statistics for free right away. So you get your memory usage. You get your process creation timestamp, so you can see when your process started. You get your CPU time, the number of open files, and the maximum number of open files that are available for you. So without further action, you can already detect memory and file descriptor leaks, which is can be a lot of problems, at least because people don't like to close their files, as I've noticed the hard way. And you can monitor whether you approach the FD system limit, whether it's a bug or not. So now let's get ready to work. And we define some metrics. So first we define a gauge, which represents the number of active requests right now. Then a histogram, and I'm lazy, so I'm using the default values for the buckets, but you should really hand-tune them to your own needs. And this histogram will measure the time spent in HTTP requests. And finally, we have a histogram for the actual analyzation of the picture. And this is how it look like. You just add these decorators, and they do exactly what they sound like. The one for the gauge will track the in-progress function calls, which translate to the in-progress requests, and the other one will just time the whole function thing. Now, you might be saying that it would be better to write middleware, because then you can get labels for the view name or for the status code. And you'd be completely right, but writing a Werkzeug middleware is a bit out of scope here, so please indulge me. So additionally, we want to measure the time to analyze, because you want to break down your times, because for all you know, the time is spent completely in authentication, and that's the main thing that takes the time. And which in turn is ostensibly not instrumented, right? It's just like before. And that's because I've decided to make it a shared package, and I want to instrument the package. Because if you have a common library in your company, you shouldn't have to instrument it 10 times if you use it in 10 applications. So again, we define a metric for the time spent in the authentication thing. Then we define one for errors. And that's because I said it's a microservice, which means it's a distributed system, which means it will fail in very inconvenient times. So we just retry and count the errors. I do realize this is not the correct way to retry in a distributed systems, but again, we have to make compromises for slides. So if this rate goes up, there's a fire burning. And as an additional red flag, we will count the the failed logins. Because if this rate goes up, it can mean also two things. That you're under attack, sometimes someone is trying to brute force some password, or you have some subtle mistake, or subtle bug in your authentication system, which manifests itself as wrong credentials, but actually just means that your database is down or whatever. So, once again, these metrics have the same name for all time series. It's always auth seconds, auth errors total, whatever. And you will differentiate them using the job label, because the job will be, in this case, maybe cat or not, or something. So, if you do this all properly, which means you instrument your shared libraries, you put web-related metrics into middleware, or even better, into whiskey containers, you're left with one extra line, which is both tolerable, but you also should not be ashamed of instrumenting your code, because it will pay off eventually. Nobody ever regretted to have too much data if they are trying to put out a fire. So now, since we are in Russia, you may be asking yourself, what about async? And I thought the same, so I wrote Prometheus Asing, which does the right thing if functions return deferreds or if they return coroutines. So it supports both async I/O and Twisted. And how it works is that it simply wraps the metrics from the official client, and that's it. So internally, it's still using the official library. I didn't want to re-implement all the math because I'm bad at math. I prefer other people to write math. So I just know how to write proper decorators, which is harder than you might think, by the way. So, additionally, there are a few goodies. So, I've written an AIO HTTP-based metrics exporter that is a lot more flexible and configurable than the one that comes with the official client, which is just using the standard library. And you can also start it in a thread. So this is useful in any Python 3 applications, not only those that you write in an async way. Additionally, it includes auto-registration with console agent. That's the one we use, but service discovery support is kept generic, so you can use whatever you want. And I should say that it's not on PyPI yet, because I have to write some tests around this service discovery thing, because it's really nasty to test. But we are using it in production, and I would love feedback if you have any opinions on the APIs I've generated and used. But everything is instrumented, so let's wrap it up. And we will look back at the promises I've made, and if I kept them. Spoiler alert, I did. So, prediction. If you build good dashboards, if you use those magic functions like predict linear, or the super new hold winters, which I'm not smart enough to explain how it works, you can predict all common problems without problems. If you fail to predict it, but you have good alert rules in place, you will get alerted in any way you want. And PromQL allows for very sophisticated conditions, as I've shown before. And finally, you do have your holistic overview. If you instrument widely, you have the data. If things get out of control, to build queries that will tell you what's going on. And you should have also dashboards that will show you how to proceed. So I guess we've covered everything. So I would like to invite you to read the page to the talk, as always. It contains all the links and projects. It contains all the topics I only brushed over, because 45 minutes is a really short time when I start talking. So please follow me on Twitter, and if you speak German, get your Variomedia. Thank you.
Questions? Really? Oh, okay.
I was about to say it was a good talk that it didn't let any questions open.
Yeah.
You ruined it.
First of all, thank you for your great speech. And my question not about your speech, but about one of your comments. You mentioned that async is about we in Russia. What that mean? What the context?
I already had an exchange about that. So it's just a matter of fact that async I/O, for reasons that are beyond me, but I have some theories which I will go into, is way more popular in Russia on the Russian-speaking languages, Russian-speaking countries like Belarus or Ukraine, than it is in the West. I don't know why, because Twisted was never that popular in Russia. So one of my theories is that one of the reasons is Andrew Svetlov, who was here last year and who wrote AIO HTTP, which is an amazing package for writing HTTP servers and clients in Asing IO. And he has been doing a lot of community building too. So he has spoken at conferences, he created a mailing list about AIO-libs, which is mostly in Russian. So he allowed both English and Russian on the mailing list, and I haven't seen many English mails on it. So this is my best theory. Because it's not like, if Twisted would have been popular here, then it would be just logical that you then change to Asing IO or something.
But maybe even because there is no Twisted in Russia, now we understood, okay, we really need to make it some kind of async. But previously in Europe, everybody is using Twisted, so they are thinking, okay, we already have Twisted, that's okay, it's working, and let it work. And in Russia, we think, okay, what is the best solution now? And we are already taking the features from CPython.
I mean, Russia has proud async tradition, right? Nginx is an asynchronous server too.
Yeah.
So, I don't know.
Thank you.
So I think everything. Oh, not everything. Yeah, it started.
Let's do it.
I'm not saying anything to MongoDB if you're gonna ask.
We will talk about that later. Thank you for the talk. I really appreciate that you spreading Prometheus to the community, because I really like it and use it a lot. And I have. I have an actual task now, actual problem, and I'm going to discover it, but maybe you can advise me something, yeah. I need to discover like AWS instances in auto-scaling groups, and they are creating and they are falling, and I want to notify Prometheus of these nodes as far as possible.
Yeah.
Maybe you know some way to do it.
Okay, so disclaimer, I don't use AWS. As I said, we run everything on bare metal. But I'm sure, because what I know about AWS is that it's pretty much API based. So REST-based, so you can get this data probably pretty easily. How many instances you have right now? So I think there will be already some AWS exporter. If not, you can write one, which will expose these numbers, like how many instances you have, how many are you permitted to do, and then it's trivial to create, just like the query I've wrote, which I've presented, where you say, are we going to run out of limits within 6 hours or something?
Okay,
So the concrete implementation I cannot really help you with, because I have no clue about AWS except.
Okay. The question is, I will generalize it. What is the way in Prometheus to do dynamic configuration for the endpoints I have?
Oh, okay. Yeah, I scratched on that. So it supports many. So if you ask me what you should use, I would say console, because I really like it. But you can use DNS. I've linked on the page. I've linked up a tutorial which goes through deploying an application using Prometheus from beginning to the end, and I think they are using DNS for service discovery, so maybe that works better for you, but I really like console.
Well,
but there are many ways. You can, I think you can even write files and everything, so this... I'm going to get back to the slide. There you go. So, there are even custom integrations. So there is no really a Prometheus way, because it is kept so generic that you can decide for yourself how to do it. So do you have some kind of service discovery in place yet?
I use plain files. Plain files to define targets and jobs.
Okay, you can do that too via custom integration. It really depends on your use case, but Prometheus is really flexible in that thing.
Okay, thank you.
Welcome.
Thanks for your talk. The first part you told about the backend, this slide. I'm wondering about some numbers, maybe. How many aggregators do I need if I got a lot of servers, for example, I don't know, 1,000 servers? And
1,000 is, I think, no problem. I have some numbers that just tuned their storage. We can look it up together later, and you can have millions of time series in one server. It's no problem. It's really effective.
What about the aggregator server? Do I get it correct? So, I mean, do I need the big aggregator server if I want to look at my metrics in one place?
Well, the thing is, imagine you have two DCs, two data centers, each with a lot of servers. So, and then you put a Prometheus in each of one, and they are scraping the targets in each DC. So of course you can, if you want to just know the data of one DC, you can go directly to the server. But if you want an overview over all of your servers, you have to aggregate them somehow. And that's, you would just set up a federation setup where you have one server that is scraping the other two. But you don't have to, it depends what data you need.
Okay, thanks.
You can talk to me later anyway, so it's no problem.
Yeah? Okay, thank you, Hynek. I think that's all. And